AC machines to three-phase induction motor subject, and here the topic is principle of working three-phase induction motor and working on load, no load and load. Objectives. So the working principle of induction motors, induction motor on no load and load. So why does the rotor rotate? The reason why the rotor of an induction motor is set into rotation as follows. When three-phase stator windings are fed by three-phase supply, then as seen from the above, magnetic flux of constant magnitude but rotating at synchronous speed is set up. The flux passing through the air gap sweeps past the rotor surface and so cuts the rotor conductors which as yet are stationary. Due to the relative speed between the rotating flux and the stationary rotor conductors, an EMF is induced in the rotor according to Faraday's law of electromagnetic induction. The frequency of the induced EMF is the same as the supply frequency. Its magnitude is proportional to the relative velocity between the flux and the conductors, and its direction is given by Fleming's right hand rule. So now, since the rotor bars are conductors from a closed circuit, rotor current is produced whose direction as given by Lenz's law is such as oppose the very cause producing it. In this case, the cause which produces the rotor current is the relative velocity between the rotating flux of the stator and the stationary rotor conductors. Hence, to reduce the relative speed, the rotor starts running in the same direction as that of the flux and tries to catch the rotating flux, but can't do so. The setting up of the torque for rotating the rotor is explained next. Here in figure A, the stator field, which is assumed to be rotating clockwise, is showing downwards. The relative motion of the rotor with respect to the stator is anti-clockwise. So now by applying right hand rule, the direction of the induced EMF in the rotor is found to be outwards. Here see, observe this one, the flux here, the flux from the stator in this figure A, the magnetic from the stator, flux from the stator, and the rotor is movement and stator movement is showing, and in the rotor the field flux. How the field will be established in the rotor only, the relative motion and in the B circuit is, say, observe this one, and here this one is, observe this one, in stator and rotor combination. The C, figure C is, see, stator and rotor combination. Observe these three diagrams, figures. Now, why does the rotor rotate? Here, so here already. So the direction of the flux due to the rotor current alone is shown in figure 1b. And now by applying the left hand rule by the effect of combined fields, stator and rotor fields in figure C, it is clear that the rotor conductors experience a force tending to rotate them in clockwise direction. Hence, the rotor is sent into rotation in the same direction as that of the stator flux field. Yeah. Now slip. In practice, the rotor never succeeds in catching up with the stator field. If it really did so, then there would be no relative speed between the two, hence no rotor EMF, no rotor current, and so no torque to maintain rotation. Now, so the induction motor will always run at a speed lower than the synchronous speed. The difference between the motor speed and the synchronous speed is called the slip. Slip is nothing but synchronous speed minus motor speed. And unslip is slip speed, and synchronous is synchronous speed of the magnetic field, and Nm is mechanical shaft speed of the motor. That is why the rotor runs at a speed which is always less than the speed of the stator field. The difference in speeds depends upon the load on the motors. The difference between the synchronous speed ns and the actual speed of n of the rotor is known as slip. Here, though it may be expressed in so many revolutions per seconds, that it is usual to express it as a percentage of the synchronous speed. Actually, the term slip is descriptive of the way in which the rotor slips back from synchronism. A percentage of slip is equal to, that is S is equal to ns minus n by ns is multiplied with 100. Now slip here, ns minus ns is called the slip. Obviously, the rotor speed n is equal to ns into within bracket 1 minus s. It may be kept in mind that revolving flux is rotating synchronously relative to the stator, but at a slip speed relative to the rotor. Induction motor on load and no load. When the induction motor is on load, the rotor rotates near the synchronous speed and the slip is very small. As the load on the motor increases, the slip speed and the slip increases. The stator current frequency and rotor current frequency relations are given the subsequent slide. Now frequency of rotor current when the rotor is stationary, the frequency of rotor current is same as the supply frequency. So, but when the rotor is revolving, the frequency depends on the relative speed or slip speed. So here, what would be the frequency of the rotor's induced voltage at n speed n? So here, Fr is equal to S into F. Now, n. So when the rotor is black, S is equal to 1. The frequency of the induced voltage is equal to the supply frequency. On the other hand, if the rotor runs at synchronous speed, S is equal to 0. The frequency will be 0. Let at any slip speed, the frequency of the rotor current be F dash, then Ns minus N is equal to 120 F dash by P. Also, Ns is equal to 120 F by P. As seen, rotor currents have a frequency F dash is equal to Sf, and when flowing through individual phases of rotor winding gives rise to rotor magnetic field. So now these individual rotor magnetic fields produces a combining rotating magnetic field whose speed relative to rotor is 120 F dash by P, that is equal to 120 SF by P, that is S into Ns. However, the rotor itself is running at speed n with respect to space. So here, and speed of rotor field in space, that is equal to speed of field relative to rotor plus speed of rotor relative to space. That means that is equal to, as here it means that no matter what the value of slip, rotor currents and stator currents, each produces a sinusoidally distributed magnetic field of constant magnitude and the constant space speed of ns. Summary is understood that for working three-phase induction motor and the relative revolving magnetic flux, rotor torque is set up by using Faraday's law of electromagnetics, Fleming's law and Lenz's law. Thank you.